So we had previously done up to this part, and now we are going to continue this video from this here onwards. And this video from here onwards basically says that we had k equals to 0 to 2n to n c k into x to the power k minus 1 equals to 1 plus x whole to the power 2n minus 1 into 2n, right? So basically this is what we had. Now we would like to make sure that we do this the right way, and let us see how we can do it. Therefore, let me just write it down first and then I'll explain. So this is what we get, and we are doing it because if you observe carefully, we do have x to the power k again by multiplying x. Now that when we differentiate, we can get a k squared in the numerator, right? So let's do that. Right. So this is what we did. What we did have basically use the differentiation for product of two functions. And again, I'm saying it again because this rules I'm not going to explain what I'm doing in differentiation and integration, because in the same video you will find the videos for differentiation and integration embedded, where you can see every time you're stuck at like a particular step which is basic and I've explained it before. You will find it in the same video at the end or in the beginning, where you can see the integration or differentiation part already explained from my previous video. So you can watch that to learn the basics again, or watch a particular part and then come back again to the solution of this problem. Okay. So now we have k equals to 0 to 2n to n c k square x to the power k minus 1 as 2n into 1 plus x whole to the power 2n minus 1 plus 2n into 2n minus 1 into x into 1 plus x whole to the power 2n minus 2. And therefore, what we do have is as follows. Right. Now we need 2k plus 1 in the denominator, right? For that reason, what we can do here is, so we can replace the x by x square in the whole of this equation. Now, one of the reasons it works is because it's an identity and it's valid for all x belongs to real numbers, okay? And that is why it does not matter, because x does not have a fixed value. The only thing that has a fixed value here is n. So n cannot be changed. Yes, well, obviously you can change n to 2n square, n to n square, and then every n in the equation will be changed. But we cannot differentiate with respect to n, because n is a fixed value after all. You can change the value of n, but not really alter it or vary it. Okay, you cannot vary the value. That's what I'm saying. So x is a variable here, and we can differentiate with respect to x. We can integrate with respect to x. So obviously we can also replace x by x square. Then the equation becomes like this. So finally the equation becomes something like this. Now it is a basically an equation in a polynomial of x square, where you have n as a natural number and stuffs like that, right? Now after this step, we need to understand what we need to do next. So well, pretty much I've done almost 80% of the problem here, but I need you to find what we need to do next. So give a thought for the problem for about 1 minute, and then we shall proceed and do the next thing. Because if you were able to understand what I'm going to do next, then make sure that like understand it clearly, that obviously I've gone through the basics of differentiation and integration and you have understood it completely. And if you weren't, no worries, you will understand it very pretty soon enough, maybe even after we have solved completing this problem and we have revised it once or twice. But try to find out what we are going to do next. So our integral is simply like this. We are simply going to integrate both sides from 0 to 1, and therefore our final answer would be an integral, which we actually wanted. We wanted to convert this into an integration, and our final answer would look something like this: k square by 2k plus 1. This should be equals to 2n times 0 to 1 x square into 1 plus x square to the power 2n minus 1 dx plus 2n into 2n minus 1 0 to 1 x to the power 4 into 1 plus x square into 2n minus 2 dx, which is our answer. Why is this useful? Because if we were to evaluate this sum for any particular n, let us say we were to evaluate it from n equals to 2. So for n equals to 2, we would have k equals to 0 to 4, 4ck, k square by 2k plus 1 equals to, now this should be 4 to 1 plus x square whole to the power 7, right? And 8 into 7, which is 56. Actually n is 2, so it's 4, and this one is not 56, it's 2 into 2 4, 4 into 3 12, right? It's 12, and this is also 3, and similarly this one becomes x to the power 4 plus into 1 plus x square whole to the power 2 dx. Now can we find the value of this things? Well, we obviously can, and these values are pretty simple to find. So because you can just expand it using binomial and use the 0 to 1 integral. Like this one is 4 times 37 by 20, and for the next one, so this one we can simplify obviously. Actually it won't be this, it won't be, a little bit different. 4, it would be 4 times 464 by 315 plus 12 times 188 by 315, and this would give us this one simplifying would give you 4112 by 315, which is approximately 13.053968, and this would be your answer. So all of these integrations can be broken down into simpler forms, and you can find the answer thereafter. So like that is how it works. That is how you basically understand these problems in a better way. Okay. So right, so this one is done. Let us do some more. Now, as you have learned in probability that the gamma function is defined as follows. This was the gamma function, right? Now what we are going to do is we are going to do some binomial coefficient sums regarding gamma function. So what we're going to do in this one is basically this. So we are required to find this value. Well, of course, this kind of values are not really what you call pretty much suspicious. But well, we can do find these values of this kind of problems. But well, we need to understand a few things. Firstly, we know that this is our basic identity that we already know, and we need to proceed from here to find the required value which we have already stated above. So I would like you to have a method for this, and I'd give you 1 minute just to not to calculate anything but just to formulate a method to reach our destination summation from this initial part. So here goes your 1 minute. Okay, so to do this problem, what we are going to do is firstly we're going to replace x by minus x. So this would be our result after replacing x by minus x, right? Now how do we go from here to here? I'll write down the solution first and then I'll explain you how do we get from there to there. And remember that beta is any real value except for like non-negative integers, non-positive integers. So let's go. So this would be the result after multiplying by x to the power minus beta plus minus of beta plus 1. So why I'm going to do this you will see soon, and I'll explain it later after that as well, but let's do it for now. And therefore this is how we do the things. Okay, now we need to understand how to do this. So let us see. This integral can be evaluated as follows. Zero to 1, 1 minus x whole to the power k by x to the power beta plus 1. Well, obviously this can be written like this. And if you remember clearly, this is the form of a beta function, and beta functions can be evaluated as follows. Now k is a natural number, therefore this becomes and this is the required answer. Therefore we can see the answer is this is the required answer, where beta is not equals to 0 or -1 or -2 and so on. And it makes sense because the gamma function is not defined at negative integer values or even at 0. So this problem again involves the beta function, the gamma function integration and stuffs like that. So obviously the gamma and beta function will also be embedded with the video, so that you can go ahead and take a look at them. If you have any problem understanding any of the steps here, how this transition of the integral occurred, how we actually managed to use this, and how this integration works, if you have any difficulty in basics of integration, so those videos will be embedded and you can watch them. And that will be it for this video, I think. So we'll continue doing some more problems in the next ones. So this is gamma distribution. Now for the gamma distribution, as I had said, we need the gamma function. So first we need to understand the gamma function. So first we shall see the gamma distribution and gamma function. So the gamma function is denoted by, I'll write you the letter for it. Denoted by gamma is like this of n, where n cannot be a negative natural number, right? That's what I mean. Obviously it cannot be 0 as well. So gamma of n, so first let us define it for natural numbers. Let us define it for natural numbers. So the gamma function is such a function that it can be used in case of natural numbers, in case of real numbers, and more so in case of complex numbers as well. So obviously what I'm going to give you is firstly an universal representation of how to use the gamma function. So it is as follows. So for n belongs to natural numbers, that is n is like 1, 2, 3 and so on, that is all the positive integers, we can define gamma of n as integral from 0 to positive infinity x to the power n minus 1 multiplied by e to the power minus x dx. So this representation is basically that of the gamma function. Now since I said we will first try to find the value of it for natural numbers, and when I say the value of it, it is a very explicit term, because as you can see we already have an integral representation and this should be enough, right? By value what we generally understand is some way of calculating it which is easier than others, which is more well known. Okay, so for example, if you had gamma of n equals to some n by 2, you would say that that is an easier form that than the integral is, because in that I'm just taking the n and dividing it by 2, whereas doing the integral would take a lot more time. So when I say simpler form, what I mean is that we are using simple elementary functions and we are not trying to use it a derivative or integral if it's possible, only then. So for this it is possible to do that. It is possible to express it without the help of any infinite series or integrals or derivatives. But how do we achieve that? Let us see. So we are going to use integration by parts. So gamma of n equals to 0 to positive infinity x to the power n minus 1 e to the power minus x dx. And you remember from our eyelet rule that algebraic functions, that is the one that stands for a, comes first, and then at the end comes e, which stands for exponential functions, right? So this would be function 1 and this would be function 2. Now since we do know the procedure for integration by parts, we can apply the following: x to the power n minus 1 multiplied by e to the power minus x dx integral, and this evaluated from 0 to infinity. This is because we are directly doing the IBP on a definite integral rather than an indefinite integral. So we do the same thing, but at the end we evaluate it from the lower and upper limits. Minus integral of 0 to infinity derivative of x to the power n minus 1 multiplied by e to the power minus x dx, and you can have another dx here because it will be used for the outer integration. So like this is basically the format. Now what we hope to achieve by this is something as follows. Firstly, this integral would mean minus e to the power minus x to the power n minus 1 0 to infinity minus, and this integral of e to the power minus x would produce a minus, which would combine with this minus and it would become a plus. So it becomes 0 to infinity. The derivative of x to the power n minus 1 is just n minus 1 into x to the power n minus 2, and it is e to the power minus x dx, right? Now we need to understand what this limit stands for, right? So let us do it here. So let us just put the 0 part first. So first let us have limit x tends to infinity. This would be minus x to the power n minus 1 by e to the power x, and when you have the 0 part, it already becomes a 0, so it's just a plus 0. So what you really have is minus limit x tends to positive infinity, of course, x to the power n minus 1 by e to the power x, and we hope to find this limit. Now observe that e to the power x is simply equal to 1 plus x square by 2 factorial plus x cube by 3 factorial. And if you wish to include the n minus 1th term, which is x to the power n minus 1 by n minus 1 factorial plus x to the power n by nth factorial, and so on, right? Because this is basically the Taylor series expansion of exponential of x. Now if we can use this expansion in a way where we can put the value directly like this, where we have limit x tends to positive infinity x to the power n minus 1 divided by, now we have this part here where we have x to the power n minus 1 by n minus 1 factorial plus x to the power n by n factorial and so on, right? So dividing up and down by x to the power n minus 1 should give us 1 divided by, so this would become 1 by x to the power n minus 1, this would become 1 by x to the power n minus 2, and this term would become 1 by n minus 1 factorial, but this would become x by n factorial. The next term would have been x to the power n plus 1 by n plus 1 whole factorial, which would rather become x square by n plus 1 whole factorial and so on, right? Now if you apply the limit individually to all the terms, what you do get is this 1 by, so this term would be 1 by positive infinity, which is 0, again a 0, and all the way up to 1 by n minus 1 factorial, which is just a constant. But then you have the terms of x, right? Then you have the terms of x square and so on. So this terms will give you a positive infinity, and all of them added will give you a positive infinity, and 1 by infinity is just 0. So that limit L here is basically 0. So coming back to our function, so coming back, we see that gamma of n is equals to 0 plus n minus 1 into 0 to positive infinity x to the power n minus 2 into e to the power minus x dx, and this would give you n minus 1 into gamma of n minus 1. This is the recursive definition. In the next video we shall try to find out how this recursive definition can be used to make the value of gamma function in terms of just n, and from the next chapter onwards we would try to see all the different properties that are present with it. There are a lot of things going on with the gamma function, and once we are clear with the gamma function, we can understand how to do problems on gamma distribution and even so beta distribution as well. So thank you for watching this video. Hello guys, welcome again to this video. So as discussed in the previous chapter, we are trying to do gamma function here, and what we had proved in the previous chapter is as follows. I will just write down the values and whatever findings we made in the last video as follows. So firstly, we defined function as follows. And we defined it for natural numbers, right? So gamma of n is 0 to positive infinity integral e to the power minus x to the power n minus 1 dx. This was gamma of n. Now what we had proved is as follows. Is that gamma of n is equals to n minus 1 into gamma of n minus 1. So we saw that the gamma function can be defined recursively like that gamma of n is basically n minus 1 times gamma of n minus 1. Now if you continue this recursion, we will have a systematic way to evaluate the value of gamma n from this recursion. But if we were to continue this recursion, this would end at a certain point where gamma of 0 would be encountered, gamma of 1 would be encountered, right? So it's better that we already find out the value of gamma of 1 beforehand. So gamma of 1 would be exactly this expression, right? Now x to the power 0 is just 1, so it will be 0 to positive infinity e to the power minus x dx. Now if we were to evaluate the antiderivative of e to the power minus x, which is minus e to the power minus x from 0 to positive infinity, so it will be minus e to the power minus infinity plus e to the power 0, which is just 1 because e to the power minus infinity is just 0. Okay, so this is gamma of 1. Now from the recursive definition, right? So what we can do is as follows: we can use gamma of n by gamma of n minus 1 equals to n minus 1, right? And now we can take different values of this left hand side expression and multiply them together, because what happens is they are a telescopic product, and when a telescopic product happens, what you do is it cancels off half of the terms, and what you're left with is only two terms. So it cancels all but 2, and those 2 terms will give you your answer. Basically what I mean is this: if you were to do an infinite product here, for gamma n by gamma n minus 1, and same thing on the right hand side for some natural number k up to some natural number k, right, where k is greater than or equal to 2. What would you get on the left hand side? So starting from 2, let us do this. Gamma 2 by gamma 1 would be the first term. Next term would be gamma 3 by gamma 2. The next term would be gamma 4 by gamma 3, like that, and the last term would be gamma k by gamma k minus 1. Observe this carefully, what I have done here. Take a moment to realize how this sum actually cuts itself off. Well, on the right hand side it would be obviously from 2 to k minus 1, which is like from 1 into 2 all the way up to k minus 1. And you see this gamma 2 and this gamma 2 cancels off, this gamma 3 and this gamma 3 cancels off. Similarly this gamma 4 will cancel off with the next part. Similarly this gamma k minus 1 will cancel off with the numerator of the previous expression, right? What will be left is gamma k and gamma 1. So what we will have is gamma of k by gamma of 1 equals to k minus 1 factorial. Therefore, gamma of k, since gamma of 1, as we had evaluated earlier, is just gamma of 1 into k minus 1 factorial, which is just k minus 1 factorial. So this is the definition of gamma of k for natural numbers k. Okay, and basically this also is valid for k greater than equal to 1, because gamma of 1 by this definition is 0 factorial, and 0 factorial, as you know, is 1. So therefore gamma of n is n minus 1 factorial for all n belongs to natural numbers n. So this much is clear, right? Now since we were very much keen on developing this formula for natural numbers, we might as well understand how to extend it to the real numbers and the complex numbers, and then we shall proceed. So what we cannot do in case of real numbers is just evaluate it in terms of factorials. That is not possible. But well, obviously, natural number or not, the definition still works, because since this happens, and this is the representation, irrespective of where n is a natural number or not, by IBP we still have n minus 1 into 0 to infinity, positive infinity, x to the power n minus 2 into e to the power minus x dx, which will give you n minus 1 into gamma of n minus 1, right? So this basically works. So what we do understand here is that, well, as long as we have n being a real number, we can still use this definition, and obviously this might not end, but still we can find a way to find all the real numbers n such that gamma of n is defined. So what it thinks here is that for s greater than 0 and s belongs to reals, gamma of s, which is equals to 0 to positive infinity, x to the power s minus 1 e to the power minus x dx, converges. So this is basically the theme. So this would imply that the gamma of s basically converges for all real numbers, and this is also true for complex numbers as well. We shall go that into it a little bit later into this lecture series, but for the next part we shall see how different properties of gamma work, how to do them, and how do we proceed with this kind of definitions, and specifically to find the value of gamma of half. So we shall see you in the next video. Thank you for watching. Hello guys, welcome again to this video. So what we did in the last chapter and the previous one, that is 2 videos have been done on gamma function, and you might now realize that the gamma function has its own properties which are specific to natural numbers and different for real numbers, because for real numbers we could not actually express it in terms of elementary functions like that of the natural numbers. But what we can do is we can always use the recursive definition. So recalling from the previous 2 chapters, results proved are as follows. results already proved are gamma of n is equals to n minus 1 factorial for all n belongs to natural numbers. So this is true irrespective of irrespective of the n basically. So n can be any natural number and gamma of n would still give you n minus 1 factorial. In a similar way, gamma of n plus 1 would give you a n factorial. Number 2, so gamma of s is equals to 0 to positive infinity x to the power s minus 1 into e to the power minus x dx, and this is true for all positive real numbers. So we did not yet get to the part where we have where we do have like negative fractional numbers, and that is also a thing. Just understand it for now that negative fractional factorials are also defined, while negative integer numbers for gamma function are basically infinity. So number 3, what is that we found that gamma s is equals to s minus 1 into gamma s minus 1 for all s belongs to real plus. Okay, and just understand that this is also true for complex numbers. S belongs to z with a 0 here because we do not include the number 0 inside the gamma function because that is basically negative infinity. Okay, right. So this would be our summaries for finding whatever we did in the previous lections. Now let us understand a few properties. And therefore, so since that can be evaluated for natural numbers, and therefore what we have is gamma, let me write down a few values. Gamma 1 is 0 factorial, which is 1. Gamma 2 is just 1 factorial, which is also 1. Gamma 3 is just 2 factorial, which is 2. Gamma 4 is just 3 factorial, which is 6. Gamma 5 would be 4 factorial, which is 24, and so on. So this would be some of the special values, and you can go on and on. Our goal eventually would be to find the value of gamma of 1 by 2, and we would try to resort to different methods in order to find this, but yes, this would be our general way of finding how to do this exact function. Okay, right. Now what we tend to do in terms of learning gamma function is that we would also learn the beta function in relation to it. Now let us evaluate a few integrals in relation to this. So number 1, 0 to positive infinity e to the power minus x cubed dx. So previously, if you remember, we had encountered integrals of the same type where the power of x may have been different, but it does not matter because they are of the same kind. But now you do know that this is called the gamma function, And previously what we would have done is we would have used IBP every time, and we would have to use it 3 times to get to the actual answer. But now what you do know is you can always express it like this: 0 to positive infinity. You have to write the power of x as something minus 1, that is 4 minus 1 for this case, dx, and this would be simply equals to gamma of 4, isn't it? And you do know that gamma of 4 is 3 factorial, and this should be equals to 6. So this integrals become quite a lot easier when you do understand the fact that the functions here this integrand can be really expressed in terms of gamma function. So you do not need to use IBP or any kinds of method again, because you just have a standard formula for evaluating this kind of integrals. Now let us do a more general one. So e to the power minus ax x to the power n dx for a greater than 0. So the solution to this one would be, firstly, we do not have the form of gamma because it should only be e to the power minus x, right? So obviously, since it should be only e to the power minus x, we have to substitute here. So which means it will be dy equals to a dx, right? And x should be equals to y by a. And the limits would not change because the limits are basically 0 to plus infinity. So just scaling the variable by a constant a would not affect. So therefore 0 to positive infinity e to the power minus ax into x to the power n dx would be equal to 0 to positive infinity, and this e to the power minus ax would become e to the power minus y, x would become y by a whole to the power n, and dx would become dy by a. As you can see, we have put all the values of x in terms of y. Now this would give us 0 to positive infinity e to the power minus y to the power n dy, and there would be a multiplication of 1 by a to the power n plus 1, and this would be 1 by a to the power n plus 1, 0 to positive infinity. What we can write is y to the power n plus 1 minus 1 e to the power minus y dy. As you can see, the integral is in the form of gamma function, so we can write it as 1 by a to the power n plus 1 gamma of n plus 1. So to summarize, what we have is 0 to infinity e to the power minus ax x to the power n dx is simply equals to gamma of n plus 1 by a to the power n plus 1 for a greater than 0 and n greater than 0. This is our result. So now you know the general formula for finding this kind of integrals, and this can be used. And if you were to find out only for using it as the natural numbers n, you can also write it as n factorial by a to the power n plus 1, which is also true. Okay, so now let us understand how to find gamma function here and how to find some of the identities, but we shall do that in the next video, where we would be looking forward to find the value of gamma of half. We will give Euler's of reflection formula as well, and then we shall understand how to do that from there on, right? Okay. Hey guys, welcome to this video, and from this video onwards we'll be trying to find out the actual value of gamma of half, and we would be trying to give you some properties on the Euler's reflection formula and if possible a proof of it. So let us see how do we achieve that goal. So let me just recall what we did in the previous chapters. What we did was as follows. What we did was we found out that gamma of n is equals to n minus 1 factorial. What we also did was to find out that gamma of z for a complex number z is 0 to positive infinity, and this holds for all z not equals to 0 basically, because since it's complex numbers we do not really want to indulge us with any kind of restrictions, but rather what we would like to say is that this holds for all z which is not 0, because what happens for gamma 0 is because it diverges to negative infinity, right? So we cannot hold it. Now there was a recursion value for all real numbers, which is just gamma of s equals to s minus 1 into gamma of s minus 1, where we had s greater than 1, right? So this was also some of the properties we had, and lastly what we saw was gamma of n by a to the power n is just the integral 0 to positive infinity e to the power minus ax into x to the power n minus 1 dx. So these were the properties that we had found during our course of lectures for the gamma function, and I have also told you before that the gamma function can also be evaluated for fractional values, right? So let's say for half integer values, which is more common. So half integer values more often than not comes in place of gamma functions, and we can evaluate them. But what we need to understand here is how to evaluate those half integer values. So I'll get to that, but before that let us solve an integral. So evaluate So for example, you are given this integral and you have said that n belongs to natural numbers, at least for this integral. So how are you going to evaluate this? So to give it a try, I'll give you 10 seconds to try, and then I shall do it on my own. Okay, so I hope you have tried it already, because this problem is not really hard one if you understand what you need to do. Because in this problem it is given that 0 to 1 minus of ln x dx, and where minus of ln x has a power of n, right? So this means that we can basically understand that this problem comprises of the fact that log of x must be substituted, right? So let us do that and hope for the best, because what I can see from this problem is, let us denote the integral by I. and we also understand that upon substituting we should get something familiar, because obviously this thing here right now here is not familiar, because we do not know how to find out derivatives of log x whole to the power n. So what I will do is I'll show you different methods for doing this, maybe in 2 consecutive videos, but I'm going to show you to do like 2 different methods for solving this particular integral. So now let y equals to minus log x. Now understand the fact that log of x is or maybe ln of x here is negative inside the interval 0 to 1. That is why a minus ln x makes sense, because otherwise the answer would be negative. So what we have done is we have used minus ln x so that we have a positive quantity to the power of a natural number. So when you have y equals to minus ln x, dy should be minus dx by x, because 1 by x is the different derivative of log of x. Now since we have this part, what we can do is dy equals to minus dx by x, and the limits we shall see that y lower should be equals to minus ln of x lower, right? Now minus ln x lower is just 0, and we know that log of 0 is negative infinity. We have talked about it earlier. So this will just give you minus infinity, which is positive infinity, right? Similarly, x lower what I mean is y upper would be equal to minus ln of x upper, and this would be just 1, and log of 1 is 0 as we know, so this becomes 0. So what the integral turns into is as follows. So the integral after the substitution is as follows. I is equals to, so the lower limit is positive infinity, the upper limit is 0, and minus of ln x is y, this is n, and dy dx dy just becomes minus dx by x, or what you can say is dx is minus x dy. Now we know x here because we understand that minus y is equals to ln of x. So x should be equals to e to the power minus y, because ln means natural logarithm with the base of y, right? So what we do have here is we can write this integral as this minus would change the course of the limit, so it will become 0 to infinity, 0 to positive infinity, y to the power n, and this would become x dy means e to the power minus y dy. And as you can see, we have reached our goal, because this is a form that we already know, right? Because this is the gamma function, and to understand it, what argument of the gamma function it is, we need to write it in this form: n plus 1 minus 1 e to the power minus y dy. So this would give you gamma of n plus 1, and since it was natural numbers, we know this should be equals to n factorial. So therefore, remember this definition of factorial: 0 to 1 minus ln of x whole to the power n dx is equals to n factorial for all n belongs to natural numbers. Or you can also say like including 0, but that's not required, because we all know that 0 to 1 dx is 1. So this one is a more familiar definition. Okay, right. What you can also understand from this definition is 0 to 1 log x whole to the power n dx would just be n factorial into minus 1 whole to the power n. because you see this minus 1 whole to the power n can come out and get divided here, and dividing by minus 1 whole to the power n is same as multiplying by minus 1 whole to the power n. And minus 1 whole to the power n, if you see clearly, if n is even it gives you 1, if n is odd it gives you a minus 1, right, which is basically the signum function. So what you can write is this is equals to signum of n into n factorial, or the sine of n into n factorial. So if the sine is odd, it will give you odd, it will give you even otherwise, right. So this will be basically our lecture for this video, and in the next video we shall try to figure out the different representations and the Euler reflection formula for ultimately finding gamma of half. Then we shall move on to the beta function, and finally when we are done with all the functions we shall understand how to do the distributions of them separately. So thank you for watching this video. Hello guys, welcome again to this video. So in this video, as we have already told, we are going to evaluate gamma of half, or we are going to try to attempt it, and let's see how much we can cover in this video, because we also need to understand how the Euler reflection formula works, because that is essential. So let me just write out what we have found in the previous videos. So our results so far are as follows. So as you can see, gamma of n is n minus 1 factorial for all n natural numbers. This was the result we found in the first video. Then we had the recursive function for gamma, which is gamma of s is basically s minus 1 into gamma of s minus 1 for all gamma is greater than 1. Then we also found out the general integral, which is 0 to positive infinity e to the power minus ax x to the power n dx for any number n. So if it were a natural number, it would give you in terms of factorial, but since it is not, we just need to understand that this argument needs to be greater than 0, that is n needs to be greater than minus 1 for this gamma function to exist here, right? And then finally we also had another integral, which gave us that this is simply equals to n factorial for all n belongs to natural numbers, right? So we haven't yet discussed the part where we can use it for fractional values, but for that, as I told you, we would try to find out the value of gamma of half. So firstly, let me state to you the Euler reflection formula. this is basically the Euler's reflection formula, and it states that if you have a real number in the open interval 0, 1, then gamma of s multiplied by gamma of 1 minus s will give you pi by sine of pi s, which can be expressed in elementary expression form, because pi is a constant which we know, and sine theta is something which we consider as an elementary function here. So what we do get is a value of gamma of s into gamma of 1 minus s in terms of our elementary functions. Now the proof of this is insanely hard, obviously, but still I'm going to let you understand how to do this proof and stuff. But for that, let us understand how this works. So firstly, the definitions. Firstly, putting s equals to 1 by 2, we get gamma of 1 by 2 into gamma of 1 by 2, because you see 1 by 2 and 1 minus 1 by 2 is also 1 by 2. This will give you pi by sine of pi by 2, right? Therefore gamma of half, since it's a positive quantity, would be root over of pi, since sine of pi by 2 is just 1. So this is the result we are talking about, and once we have this result, you will see it is easier to connect it to the more fractional values of gamma. So let us take a few examples understanding how it works. So let's say we were to evaluate gamma of 5 by 2. Okay, so to evaluate this gamma of 5 by 2, what we can do is as follows. We can write this as, using the recursive property, we can write this as gamma of 5 by 2 minus 1 into gamma of 5 by 2 minus 1. So this here becomes 3 by 2 multiplied by gamma of 3 by 2. So see how we have used the property of recursion here, because we defined that this is valid for all is greater than 1, right? Therefore (3 by 2) multiplied by, now the gamma of 3 by 2 can again be evaluated in the same way. It can be written as 3 by 2 minus 1, as long as the argument is greater than 1 we can do that, into gamma of 3 by 2 minus 1. This would give you 3 by 2 into 1 by 2 into gamma of 1 by 2. Now since we do know the value of gamma 1 by 2, it becomes relatively simple, because it becomes 3 by 4 root pi, which is the answer, right? So as you can see, this gamma function is basically how we can find out all the different formations, and we can find out that all the half integer values can be evaluated exactly in terms of gamma of half. Let us take another example in terms of an integral now. Let us say you were given the integral 0 to positive infinity so as we know from our previous discussions, that this can be written as 0 to positive infinity e to the power minus 2x into x to the power 5 by 2 minus 1 dx, right? And if you see the integral that we evaluated right here, you see that it is equals to, when you have a power of x which is x to the power n, gamma of n plus 1 by a to the power n plus 1. So actually what we can do is we can use this representation directly, and we can write it as gamma of n plus 1 by a, here a is 2 to the power n plus 1. So what we get is gamma of 5 by 2 by 2 to the power 5 by 2. But we know the value of gamma 5 by 2, which is 3 by 4, and we have 2 to the power minus 5 by 2 into root pi. This becomes 3 by 4 means 2 square. This means 2 to the power 5 by 2 into root pi. What it becomes is 2 plus 5 by 2 is basically 9 by 2. So 3 by 2 to the power 9 by 2 root pi. and this is the answer for this integral. So having the value of gamma of half really lets you lose all your attention to different details, and it lets you evaluate all these integrals directly using some standard formulas. Of course, we have proved those standard formulas before, and if required, you may also have to prove some of the results when you are trying to use these formulas, at least for once, in your answer sheet or wherever you're trying to do it, maybe in your publication, maybe somewhere else, but you need to prove it at least once, I think, because that is a good practice always, to use a formula that you're going to use repeatedly, to prove it at least once somewhere around. And this would actually give us the idea about how to evaluate these integrals. And finally, I would just give you a whisker of an idea of how to evaluate or prove the Euler reflection formula. So the formula was so it is 0 less than s less than 1, and what we can do is we can use double integration to evaluate this, right? So basically what we can do is as follows. We can write that gamma of s is basically 0 to infinity e to the power minus x, x to the power s minus 1 dx, and what we can write is gamma of 1 minus s is basically 0 to infinity e to the power minus a, let's say y, and y to the power 1 minus it's not really, it's basically 1 minus s minus 1 dy, or this can just be written as 0 to infinity e to the power minus y, y to the power minus s dy. And using these two different representations of the integral, we can transform this into a we can multiply this and transform it into a double integral, and then we can evaluate it. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.